Imagine a substance that doesn't melt, leaves not a single drop of water, and simply vanishes into thin air. It can freeze anything within seconds, create thick white fog that rolls across the ground, and even stop life itself if handled carelessly. Dry ice isn't just cold, it's a controlled force of nature that humans have learned to harness. Deep beneath the hum of compressors and swirling clouds of white vapor lies a process that seems like magic, where gas transforms into solid matter at -78 degrees. But where does this gas come from on an industrial scale? And why is dry ice production considered a genuine environmental miracle? Watch until the end and you'll see how something so cold can become one of the hottest businesses in the world. Industrial dry ice is nothing other than solid carbon dioxide, which freezes at the extreme temperature of -78.5 degrees Celsius. Put simply, it's the very same carbon dioxide we exhale with every breath, which plants absorb and which gives fizz to your favorite carbonated drinks. Unlike ordinary ice, which melts into water, dry ice possesses a remarkable property: sublimation. It transitions from solid state directly to gas, bypassing the liquid phase entirely. That's why it's dry. It leaves no puddles behind, simply disappearing into invisible gas. This unique ability to cool instantly and evaporate without trace has made it indispensable across dozens of industries. In medicine, dry ice is a genuine guardian of life. It's used for transporting vaccines, donor organs, and blood, where every second's delay and every extra degree could cost a life. In cryotherapy, it's applied for targeted freezing and removal of warts. In the food industry, it's become a guarantor of freshness. Frozen products, meat, and ice cream are transported in containers filled with this cold wonder. And in the world of entertainment, dry ice is the chief instrument for creating magic. The thick, heavy fog rolling across stages at concerts and theatrical performances, or smoking cocktails in bars, all of this is the work of dry ice, which creates impressive visual effects when it contacts hot water. Dry ice production takes place at cryogenic plants. These facilities occupy enormous industrial areas, comparable to several football pitches. At the center of the site stand gigantic cryogenic tanks, steel towers up to 50 feet high, capable of holding up to 100 tons of liquid carbon dioxide. Inside the workshops, there's a constant hum, powerful compressors and hydraulic presses at work. From the giant tanks, liquefied gas flows through thick, frost-covered pipes into the very heart of production, the pressing installations. These machines are absolute monsters, capable of compressing up to 500 kilograms of dry ice in a single minute. When liquid carbon dioxide under enormous pressure bursts from the nozzle into a chamber at normal atmospheric pressure, rapid expansion occurs. This process, known as the Joule-Thomson effect, causes the gas to cool and freeze instantly, transforming into loose, snow-like dry ice. A cloud of thick white vapor rises above the pressing chambers as powerful hydraulic presses, with force measuring hundreds of tons, compress this snow into dense, heavy briquettes or fine pellets. Conveyor belts move continuously, carrying away the icy blocks. They pass through refrigerated tunnels where temperature is kept below -40 degrees. Automated machines slice large slabs into smaller pieces or transform them into pellets the size of peas. Packaging machines work at lightning speed. Precisely calculated quantities of dry ice are poured into special polystyrene thermal containers, from small 1-kilogram packets to enormous containers holding hundreds of kilograms. Automatic sealers hermetically close the packages to slow the sublimation process. In 1 hour, a single such plant can produce about 5 tons of product. Now imagine the working conditions in this frozen kingdom. In zones where presses and packaging lines operate, temperature stays below -40 degrees. Workers here resemble polar explorers. They're dressed in multi-layered thermal insulation suits, wearing special gloves on their hands, since direct contact with dry ice causes instant and extremely painful burns. On their faces are protective goggles and masks, as high concentrations of carbon dioxide in the air can cause dizziness and suffocation. Because of this, powerful ventilation systems must operate in the premises, constantly refreshing the air and maintaining safe oxygen levels. To avoid hypothermia, workers labor in short shifts, alternating work in cold zones with breaks in warm restrooms. Many processes are maximally automated to reduce human presence in extreme conditions. But even with such protection, work at these plants demands incredible endurance and the strictest adherence to safety procedures. So where do plants obtain carbon dioxide in such colossal quantities? The secret is that they don't produce it specially, they collect it. It's a byproduct of other major industrial processes. The main sources are ammonia and fertilizer plants, breweries where gas forms during fermentation, as well as petroleum refining and cement works. Rather than releasing this carbon dioxide into the atmosphere, it's captured by special installations. The gas then undergoes multi-stage purification from impurities, is dried and compressed under high pressure, transitioning to liquid state. This process is the brightest example of industrial symbiosis and circular economy, where waste from one production becomes valuable raw material for another. But for all its usefulness, dry ice is a substance requiring extreme caution. Its temperature is so low that it can cause serious burns upon contact with skin. But the main danger lies in its sublimation. Whilst evaporating, dry ice displaces oxygen from enclosed spaces. Being in an unventilated room where large quantities of dry ice are evaporating can lead to suffocation. Tragic cases are known where people suffered fatal poisoning using dry ice to create fog and enclosed swimming pools. Therefore, working with it requires strict adherence to safety rules, good ventilation, use of protective gloves and goggles. Now let's glimpse into the future, because dry ice has an incredibly exciting one ahead. Right now, scientists and engineers are developing technologies where dry ice plays a key role. For example, in fire suppression. Unlike water or foam, dry ice doesn't conduct electricity and leaves no traces, making it ideal for extinguishing fires in server rooms, museums, or power stations. Dry ice pellets are sprayed onto fire, instantly cooling it and displacing oxygen. Another direction is cryogenic cleaning or blasting. Tiny dry ice pellets are fired under high pressure at contaminated surfaces. Striking them, they instantly evaporate, and the micro-explosion caused by rapid gas expansion literally blasts off dirt, paint, or rust without damaging the surface itself. But the most fantastic prospect is terraforming planets. Scientists are seriously considering the possibility of using carbon dioxide, which in solid form covers Mars's polar caps, to create an atmosphere. By melting Martian dry ice using nuclear explosions or gigantic mirrors, one could trigger a greenhouse effect that would warm the planet and make it habitable. So this cold, smoking material that we use today for cooling drinks might one day become the key to transforming the red planet into our second home. This proves that even the most ordinary-seeming substances conceal within them boundless potential that humanity has yet to unlock. Every year, the world extracts over 8 million tons of gray, unremarkable ore, but only a tiny fraction of it undergoes an incredibly complex, almost alchemical journey to become a metal capable of withstanding even spaceflight. Titanium isn't just a metal. It's a substance born in hell from fire, chlorine, and magnesium at temperatures exceeding 1,000 degrees Celsius. Its first form looks like light ash, but from it they create the invisible skeleton of aircraft, eternal implants, and rocket engines. How does a chunk of dirty rock transform into a material stronger than steel yet lighter than aluminium? Watch to the end, and you'll see how an ordinary stone passes through chemical purgatory to become the heart of modern civilization. The history of titanium is the story of a ghost metal that remained hidden in plain sight for decades. In 1791, British clergyman and amateur geologist William Gregor, while studying black sand on the Cornish coast, discovered traces of an unknown element within it. But only 4 years later, in 1795, the great German chemist Martin Klaproth independently discovered the same element and named it titanium, after the mighty Titans from ancient Greek mythology. However, despite its thunderous name, the metal remained elusive. For nearly a century and a half, it slumbered in chemistry textbooks, resisting attempts to isolate it in pure form. Only in the 20th century, thanks to breakthroughs by American chemist Matthew Hunter and Dutch scientists, did humanity finally manage to touch pure titanium. From the mid-20th century, with the onset of the Cold War and the space race, titanium transformed from a laboratory curiosity into a strategic material. The United States, recognizing its colossal potential, invested enormous sums into its production. Titanium became the foundation for the legendary spy plane SR-71 Blackbird, capable of flying at the edge of space, and found its place in the construction of Apollo spacecraft. Titanium production begins with mining its ores, ilmenite and rutile. These minerals are found in the sands of Australia, Canada, and South Africa. After extraction, the ore undergoes multi-stage enrichment. It's washed, screened, separated from waste rock using magnets and gravity, yielding a dark, heavy concentrate. But this still isn't metal. This is merely titanium oxide, where it's firmly bound to oxygen. To break these molecular shackles, the concentrate is sent to chemical hell, into fluidized bed reactors. Here, at temperatures of 1,000 degrees Celsius, gaseous chlorine is blown into a boiling layer of ore and coal. A fierce chemical reaction begins. Chlorine tears titanium away from oxygen, forming a volatile compound, titanium tetrachloride. This caustic, toxic substance is then repeatedly distilled, purifying it from impurities to near-perfect purity. The next stage is the heart of the entire process, named after its creator, William Kroll. Into a sealed steel sarcophagus filled with inert argon gas, molten magnesium is placed. Then purified titanium tetrachloride is slowly fed in. A chemical duel begins. Magnesium, being a more reactive metal, literally rips chlorine atoms away from titanium. As a result of this battle, pure titanium settles at the reactor's bottom, but in the strangest and most unremarkable form imaginable. This is sponge titanium, a porous, lightweight gray mass that looks like frozen foam or pumice. It's brittle and utterly unlike strong metal. But inside this ugly porous sponge lies all the future might. This sponge is extracted, crushed, and then pressed under enormous pressure into dense briquettes. And only then is it sent to its final transformation, into the melting furnace. To transform sponge briquettes into a monolithic ingot, they're melted in vacuum arc furnaces. This is necessary because at high temperatures, titanium absorbs oxygen and nitrogen from the air with incredible greed, instantly making it brittle. Inside a sealed chamber, a powerful electric arc, like lightning, melts the briquettes, and liquid titanium flows into a copper, water-cooled mold. To achieve perfect uniformity, this process is repeated twice, sometimes even thrice. The result is a gleaming, silvery ingot of pure titanium, ready for further processing. Just look at this incredible transformation, from porous, lightweight sponge to dense, shining metal. But pure titanium is merely the beginning. To create materials for aviation and space, it's transformed into alloys. To molten titanium, like spices in a chef's dish, other metals are added: aluminium for lightness, vanadium for strength, molybdenum for heat resistance. Thus is born, for example, the most famous titanium alloy, T6Al4V, which became the workhorse of the aerospace industry. These alloys are remelted several times to achieve perfect uniformity. The next stage is mechanical processing. Giant ingots are heated red hot to make them malleable and sent under presses or rolling mills. With incredible force, machines bend the metal to their will, transforming it into sheets, rods, beams, and wire. From these semi-finished products, the most complex parts are then cut, turned, and milled. But that's not all. In recent years, additive technologies, or three-dimensional printing, have entered the game. Special printers sinter the finest titanium powder layer by layer with lasers, growing parts of such complex geometry that traditional methods cannot achieve. This allows creation of lighter and stronger components for aircraft and rockets, saving up to 40% of weight. Every finished part undergoes the strictest control. It's X-rayed, scanned with ultrasound, checking for the slightest internal defects. In aviation, titanium has become indispensable. From it, they make up to 15% of a modern passenger airliner's weight, landing gear, wing elements, and of course, engine components. This significantly reduces the aircraft's overall mass and increases its fuel efficiency. In the medical field, roughly 70% of all implants, such as artificial hip joints or dental prosthetics, are made from titanium. Its unique biocompatibility means the human body doesn't reject it, allowing bone tissue to literally grow into the implant surface. This is a metal that becomes part of a person. Thus, having passed through fire and chemistry, an unremarkable stone transforms into high-tech material that pierces the heavens, explores space, and restores people's ability to move. But titanium conquered not only the sky, but also the darkest ocean depths. At the height of the Cold War, Soviet engineers created something unthinkable: submarines of Project Lyra, known to NATO as Alpha. Their hulls were made entirely from titanium. This allowed them to dive to depths unreachable by the enemy and develop underwater speeds exceeding those of torpedoes. These goldfish, as they were nicknamed for their incredible cost, became underwater phantoms, invulnerable to magnetic detectors and capable of escaping any pursuit. Titanium is the only material capable of withstanding the colossal pressure at depths of 800 meters whilst remaining sufficiently light. Moreover, its absolute resistance to corrosion in salt water makes it an eternal material for the marine element. So what's titanium's main secret, promised at the beginning? It's not just its strength or lightness. Its true magic lies in its ability to self-heal. Every time titanium's surface is scratched, it instantly reacts with oxygen from the air or water and covers itself with the thinnest, invisible, yet incredibly strong film of titanium oxide. This is a sort of invisible armor that instantly regenerates when damaged. It's precisely this film that makes it absolutely inert, preventing it from reacting with the human body or aggressive environments. But this superpower has another side, another secret. During mechanical processing, if proper technique isn't followed, fine titanium swarf can spontaneously ignite. This white fire burns at such high temperatures that it's impossible to extinguish with water or sand. Taming titanium is playing with fire in the literal sense. And only those who've mastered this art can make this mythical metal serve humanity.